Hello there, everyone. Welcome back to another calculus video. So today we are learning about trigonometry and its role in integration. We're learning about really special trigonometric integrals as the topic of today's lecture. And we were planning on diving into this problem and giving it a try, but it ended up being, I felt, maybe a little too long and a little too complicated for an introductory lesson. So as promised, I decided to upload a solution that's separate from the actual lecture so that we're not eating up too much class time with a particularly long problem. So that's the main goal of this video. We're just going to be doing this problem and I'll walk you through the entire solution. So what's the goal here? We know that the goal is integrating, but how the heck do we do that? How the heck do we write this in such a way that it's able to be integrated? So we've learned quite a few techniques up to this point. Aside from basic integration, we have integration by parts, we have substitution. We have all of these tools at our disposal to help us integrate different types of things. So our goal by the end of this class is to be able to look at an integral and understand exactly how to integrate it, because it may not always be clear. We may have to manipulate it a little bit first before we can understand exactly how to tackle it. So the goal of this chapter is to do a little bit of simplification before even diving into integration, before even attempting the calculus part of this. It's always in our best interest to see if we can manipulate something using trig identities or maybe some of those algebra rules from pre-calc before we dive into the actual integration part, the actual calculus. So we're going to be deciding what trig identity would be really useful to turn this into something that can be integrated. But before we even do that, let's remind ourselves what the derivatives of the trig functions are, because if we know what the derivatives are, we also have a pretty fair idea of what the integrals are. So we know that the derivative of the sine function is cosine. We know that if we were to go backwards, if we were to do cosine, the derivative of cosine would be negative sine. We don't really need to write that. Derivative of tangent of x is secant squared of x. So that means that the derivative of cotangent would be negative cosecant squared of x. And then the derivative of secant of x would be secant of x times tangent of x. And because we know what the derivative of secant is, we also know that the derivative of cosecant is going to be negative cosecant of x times cotangent of x. So if you know these three, you know the other three as well. So our goal is to take a look at what we have, see which of these categories it's going to fall into, and then decide what might be the best call, the best judgment call when determining how to integrate this function and how to rewrite it. We know sine and cosine are derivatives of each other. We have something involving sine and cosine in our integrand. So we're going to see if we can somehow write this so that it's just a single power of one of them, because substitution works if we have a fifth power and a second power. Just doesn't work very well at all. Ideally, we want something like this. One of them must only be a 1. We can't have this, for example, be anything but a 1, otherwise substitution won't work. We could have u would be cosine of x, for instance. So this would be u to the 4th power. And then this would be du. It doesn't work having this be squared because we can't have a du squared. It's illegal, for lack of a better word. It's illegal in the laws of mathland. So we can't do that. We always have to be du, be a single power only. So that's why we can't have this be a 5th power and this be a 2nd power. One of these has to be just a single power. So the goal of this video is to understand how to reduce either one of these into just a single power so that we're able to use substitution. So we're going to be using this identity, and we're going to be using this derivative, and in addition to that, we want to decide what identity might be useful. So to me, because we have powers of sine, we have powers of cosine, to me it looks like we're going to be using one of those Pythagorean identities, specifically the one that says sine squared of x plus cosine squared of x is equal to 1. Handy little thing that's going to be really useful in this chapter. We're going to be seeing this quite a bit. So let's decide if we want to reduce the sine down to the first power somehow through some manipulation, or if maybe we want to do that to cosine. So we have an odd power of sine, we have an even power of cosine, which seems like a pretty clear indication. It may not be clear right away, but the more we work through this section, it'll be clear over time that the odd power, it's best to take the odd power function and reduce that to a single power. It's not so easy to do with the even power. I mean, it is possible, but it's much more faster and much more efficient to take the odd power and reduce it to a single power. How do we do that, though? Well, because we know that sine is the one we want to reduce to a single power, we're going to write this as a single power times another power. So in other words, we can break this up into a sine of x times a sine to the fourth power of x, and that works pretty well. So all I'm doing is I'm expanding this and we get this whole thing. The cosine is going to be unchanged for now. We're going to leave that part alone. So the next step is figuring out what kind of manipulation we can do to take only this part, only the sine to the fourth power of x, and make this look like not a sine, but turn this into a cosine somehow. Because if we turn this into a cosine, life is good. If we turn this into a cosine, we only have one sine and then the rest of it is cosine. Really, really simple to do from that point on. It's just a simple U substitution problem. But before we can even talk about that, we're going to have to kind of just strategize for a bit, just take a minute and think about how we could possibly turn this sine to the fourth power of x into something involving a cosine. So we're going to need to use this identity once again, or I guess for the first time. We haven't used it yet. We're going to be using it for the first time now. We have sine to the fourth power of x. So we're going to need to solve this first for sine squared of x, and then somehow turn it into sine fourth of x. So let's subtract cosine squared x from both sides. We're going to get sine squared of x equals 1 minus cosine squared of x dx. Or not dx. Sorry, got a bit ahead of myself there. But this is what we get when we modify our trig identity. So if we had just sine squared of x, cosine squared of x, we'd be golden. We'd be good to go. But we don't have that, so we're going to need to think about what way we need to think about how we could possibly turn this into sine to the fourth power of x. Well, I'm thinking we just want to square it. We want to square this, and we want to square that. So then what we have is we have sine to the fourth power of x equals, we're going to apply our binomial theorem to this next part. We're going to make this 1 minus 2 cosine squared of x. And then this is going to be plus cosine to the fourth power of x. See if I have enough room to write that. Wonderful. All right, so we were able to successfully turn this into the sine of the fourth power of x. And the reason why it's so nice to be able to do that is because now we have something we can substitute. We're going to turn this into all of this that appears on the right side of this newly derived identity. So let's go ahead and rewrite this. We're going to make this sine of x times all of this. It's going to be times 1 minus 2 times cosine squared of x plus cosine to the fourth power of x. Oops, running out of room. Move it down a little bit. There we go. And then at the end, we have the cosine squared of x dx. So what do we want to do from here? You might think, hey, Justin, you're crazy. We took something that looked complicated and you made it even worse. You made it even uglier. What the heck are we supposed to do now? Well, it does look ugly. Yeah, I'll admit that. But it'll be easier if we distribute it and we break it into separate terms that are able to be easily integrated. So we have a sine appearing before this group. We have a cosine squared appearing after this group. So let's go ahead and distribute the sine and the cosine squared to each of these three terms and integrate them separately. So as a result, we're going to get sine times cosine squared of x as one integral. Oops, sine of x times cosine squared of x. Our next term is going to be negative. We're going to have minus 2 times the integral of, this is going to be cosine squared of x times another cosine squared of x. That's going to get us cosine to the fourth power of x, and we're still going to have the sine from before. So we're going to have a sine of x times cosine to the fourth power of x. And then our very last term is going to be positive. We're going to have plus the integral of sine of x. And then we're going to combine this cosine to the fourth power of x with this cosine squared of x. If we multiply those together, we get cosine to the sixth power of x. So oftentimes in math in general, but mainly in integral calculus, we have to make things uglier before we can make them nicer. We have to turn something more complicated before we even have the hope of being able to integrate it. And this is one of those examples. This is actually a common theme in computer science. A common theme in computer science is that oftentimes in order to solve a really difficult problem, you have to break it up into simple, smaller, more manageable problems and solve each of them separately. They call that modularity. So we're applying that concept here in calculus. We're taking something that looks fairly simple, but we don't know how to integrate it, so we expanded it. We made it look much longer and much scarier looking, but then we're able to break it into three simple, manageable problems. So that's why it's such a useful strategy, being able to break up a problem into simple, smaller problems. Modularity is a great thing to have on your side. So from here, we can see that it's just a simple u substitution we have to do in each of these three terms. So the u is going to be the same for all of them. We're going to have u is going to be cosine of x. And we have du is equal to negative sine of x. But instead of writing du as negative sine of x, I'm going to make the du negative. I'm going to make the sine of x positive. You might be thinking why we want the cosine to be u and not the sine. Well, if we make the sine u, it doesn't work very well. Because here, I'll just show you what happens real quick. If u is sine of x, of course, du would have to be cosine of x dx. And the quick substitution would yield the following. It would yield the integral of u, and then this would be du squared. And this is illegal. We can't have any du other than a single power. We can't have du to the second power. And if you go farther in math than this class, I mean, we're not really going to be getting into why this is not okay in Calc BC. But if you take higher level math classes, like I think some of the analysis classes get into why that's not okay, you will see why it's much better to have u be cosine of x and du would be negative sine of x. So let's go ahead and substitute. So we're going to have a negative out front. We have negative du, so we have to make sure there's a negative out front. And then we have sine of x dx. They come together and form du. And then we have cosine squared of x. This is going to be u squared. So we have cosine squared of x is u squared. And then this first factor and then this last factor come together to form collectively a du. So sine of x times dx is going to be du. All right, and then something similar applies to the next two terms as well. The only thing that's going to be different is that we have a higher power of cosine. So instead of u squared, we're going to make this u to the fourth power du. But because we already have a negative sign, we're going to have two negative signs. It's actually going to turn into a plus 2 times the integral. Plus 2 integral of u to the fourth power du. And then same thing applies to this last term. So the last term is positive. We have a negative du, which means the last term is going to turn into a negative term. We're going to have minus the integral, and then we have u to the sixth power du. And then from here, it's pretty straightforward. We know exactly how to integrate things like this. We're going to pretend that it is just x squared instead of u squared. So if we integrate x squared, we get 1/3 x to the third power. So we're going to have 1/3 u to the third power this time. And u is just cosine of x. So we have 1/3, negative 1/3, cosine of u to the third power. So, no, sorry, just u to the third power. So this would be cosine cubed of x. And there's supposed to be a plus c because this is an indefinite integral, but I'm just going to add 1 plus c at the end to account for all three of these. So after this, we're going to add 1 to this next power. We have u to the fourth power. We're going to make it 1/5 u to the fifth power. Because we have a 2 out front, it's actually going to turn into a 2/5 u to the fifth power. And u is still going to be cosine of x. And then we have another one. We have minus, this is going to be u to the 7th power, 1/7 u to the 7th power. So u is cosine of x, so this is going to be 1/7 cosine to the 7th power of x plus c. There you have it. Not terribly difficult, but when you're learning this for the first time, it's confusing. You don't know exactly how to write this so that it can be integrated. So u substitution is probably going to be our most widely used integration strategy throughout this entire chapter. So whenever you're faced with a problem like this, your first thought should be, well, how do I write this so that there's one function to the first power? Or sorry, how do we write this so that there's one function and then we have the derivative of that function to the first power? So always be in that mindset. Always see if you can set it up like that and then integrate.